Hi everybody, this is Cal with section 2.5, Intervals. This is the end of chapter 2 for us, and just going to basically investigate the idea of intervals a little bit. We start out on the bottom of page 46, and this is all just terminology and notation, and you should really be familiar with this notation already, hopefully. So go ahead and familiarize yourself with everything on this half page. It's all just basic stuff that you need to know that I will be really happy to not have to spend time on in class. And that goes on to the top of 47. There's a pretty important warning at the top of 47 that infinity and negative infinity are not elements of R. They are not numbers. They're symbols that we use in interval notation. Okay? Now, we're going to get a little bit into more of the theory of intervals. We have the characterization of intervals here with the characterization theorem 251. It says that an interval is defined by the property that for any two numbers in that set, so if you have a set that has the property that if any two numbers are in the set, then the interval between them is in the set, then that set is an interval. So parse that, draw a picture, and read the proof. The proof is pretty important. It's a really good demonstration of why you need SUPs and INFs to talk about intervals. I recommend that you try to understand what's going on in case 1 and 2 and try to fill out cases 3 and 4 on your own. Then we get into the idea of nested intervals. Nested interval is a chain of intervals where each one includes the next. Do read the example at the bottom of the page. Understand what it's talking about. That's a pretty important idea. You should also try to, where the book says prove this in parentheses, you should try to prove it. This is a nice little example at the bottom of the page. Now, with that first example, the nested intervals have a common point. And then we have an example where there is not a common point in the middle. And you should read why. You should try to figure out why that's true. Now, 252 is a really important property. It says that if we have a nested sequence of closed and bounded intervals, so special type of nested sequence of intervals, then there is a number in their intersection. They do have a common intersection. And by the way, the really squiggly squiggle number is called xi. It's spelled xi. It's probably the hardest Greek letter to write. We will use that for this proof, so yeah. The proof of the nested intervals property is pretty interesting. Again, it uses SUPs in a pretty implicit way, or at least endpoints of sets, and then the supremum of a sequence of endpoints. A really good proof to try to draw a picture of. We'll probably spend a little bit of time on this proof in class. Do read and understand theorem 253 and its proof. And finally, we get into the uncountability of R. And we have a little bit of setup to get there. So first, we do a first proof with that R is not countable by using the nested intervals property. And this proof is okay, but it's not so heavily intuitive. So read it, and again, if we have time, we'll talk about it, but I really like the second proof that's coming down the road. So, keep reading relatively carefully after this proof on the rest of the page. The notes here are interesting, but not, totally necessary. The section on binary representations is pretty cool. It gives us, the mathematical how-to of how we define binary representations. The note near the bottom of the page, starting with conversely, each sequence of zeros and ones is the binary representation of a unique real number. do read and understand what that's saying. That's pretty important to the argument that we're developing here. We use this idea of binary representation to develop the idea of decimal representation. And what we have in this section is really a fancy write-up of what you've known about real numbers forever. Read it, make sure you understand what it's saying. And we get here at the bottom of page 51 into a discussion of periodic decimals, and the fact that a positive real number is rational if and only if its decimal representation is periodic or terminating. But terminating is a type of periodic because you just have repeating zeros forever after the point that it terminates. So this is a reasonably important bit here, and we use that to get Cantor's second proof of the uncountability of R. I absolutely love this proof. It's one of my favorite proofs in the entire course. We'll certainly spend time on it in class. You'll notice that this has the heart of this proof is very similar to the proof of Cantor's theorem 1.3.13, where we were talking about if each element in a set corresponds to a subset of that set. We're dealing with power sets, remember. We're kind of forcing a problem because each element, we look at the set of elements that are not in their corresponding set. It's this Russell's paradox. If the barber is the person who shaves everybody who doesn't shave themselves, and who shaves the barber? We're using that same general idea here. If we did have an enumerated list of all of the real numbers, we'd be able to write them out here, and then we could actually construct a number that's not on this list just by changing all the numbers on the diagonal here. So I love this proof. Try to understand what this proof is saying, why it works, why it creates a contradiction. I think it's pretty fantastic. So I strayed a little bit there, but that ties up section 2.5. So enjoy your reading, and I'll see you next week.